Okay, let's take a look at the problem at the end of chapter 8, and it's given as table 8.2 for question 8.2 at the end of the chapter. And so if you look at the end of the chapter, you see the exercises, and exercise 8.2 has a table called regression results for exercise 8.2, and these are the regressions. Our dependent variable is the log of the price of a house. We have a sample down in the footnotes. Actually, this is probably a made-up regression, so it doesn't give us what the sample size is. But we have price as the sale price of a house, size is the size of the house in square feet, bedrooms is the number of bedrooms, pool is a binary variable for whether the house has a pool, view is a binary dummy variable whether the house has a view, and the condition is a dummy variable for whether a real estate agent reports the house to be in excellent condition or otherwise. So those are our variables. We have 5 specifications. We note that the R-square doesn't change too much across the specifications, and that's probably because the size of the house, the square footage of the house, is probably the main explanatory variable in these regressions that determines the price of the house. And the pool and number of bedrooms and whether it has a view are going to be affecting the value of the house more at the margin, but mostly a 1,000 square foot house is completely different from a 2,000 square foot house, which is very different from a 3,000 square foot house, and that's the size is the main driver of the price. So we remember here we have log price, so it's a log linear form. So we interpret the coefficients by multiplying the coefficient by 100 and interpreting that as the percent change in price. So we have our coefficient on size here. If we multiply that by 100, then when size goes up by 1 square foot, price goes up by 0.042%. That may seem like not very much, but remember what I just said. The size changes that we're talking about here are 1,000 square feet changes. A small house is 1,000 square feet, a big house is 2,000 square feet, a really big house for a big family is 3,000 square feet, or for a really rich person wants 3,000 square feet. And so what we really need to do is ask what's the effect of 1,000 square foot change. So if a 1 square foot change leads to a 0.042% change in price, then 1,000 square foot change leads to a 42% change in price, is associated with a 42% change in price. So that's how we interpret the coefficient. Now in their regression, they're also going to have the log specification and the square of the log specification. And then have the pool and view specification, and then pool and view interacted. Now in the question, in the problem, there's a set of questions. So first, compare columns 1 and 2. Is it better to use size or log size to explain house prices? And we look here between 1 and 2, and we see that the R-square is basically the same, and the coefficients are basically statistically significant in both of these equations, so there isn't that much reason to prefer one to the other. The log specification is slightly higher R-square, so maybe we would prefer that. So that's question 1. Question 2 asks us, using column 2, what is the estimated effect of pool on price? So we go back to equation 2, and we see that pool has a coefficient of 0.07, but we want to interpret the coefficient the right way because our outcome variable is the log of price, and so we interpret that coefficient as being a house having a pool has a 7% higher price. Remember, we multiply the coefficient by 100 and treat it as a percent. So house having a pool is 7% higher price than house not having a pool. Our next question asks, the regression for column 3 adds the number of bedrooms to the regression. How large is the effect? Is the effect statistically significant? And if it's not, why not? Or why is the effect so small? So we go here to regression 3, and we're looking now at the coefficient on bedrooms, and we see that the coefficient on bedrooms is 0.0036. This standard error is 0.037, so this is definitely not statistically significant. The t-stat is going to be about 0.1, so we're certainly not going to have a p-value less than 0.05. So it's not statistically significant, and we might say, well, why isn't it statistically significant? And that's because we're already controlling for the size of the house. So bedrooms isn't really adding anything in terms of the value of the house, since it's really the size that's determining how valuable a house is, rather than the number of bedrooms. If you have a big house, you can always put in a few walls and add more bedrooms. That's relatively inexpensive to do, and so that's not the number of bedrooms is not the main driver of the price of a house. Instead, it's its size. So there we go with that question. We move on then to, is the quadratic term log size important? Well, let's go back and look at our coefficient. Here in equation 4, we have log of size and then the square of log of size. And we notice the coefficient on log of size is 0.0078, and its standard error is 0.14. So right away we can say, well, it's not even statistically significant, so we can't reject the null hypothesis that the coefficient is equal to 0. But suppose it were statistically significant, what's its magnitude? That's what we're interested in thinking about. What's the magnitude of this? Well, let's simplify it and say that it's 0.57 times the size. Actually, and I realize now this should be the log of the size, right? It's not the size, so I think I was doing the math wrong here, because I thought it was the... it is indeed the log of size, not size squared. So my interpretation here isn't going to be right, but let's go ahead anyway. Suppose it was just the size rather than the log of size. So we have this quadratic expression, and then we can ask, well, if size is equal to 1,000 and then size increases to 1,100, what's the effect on the outcome? So we hold everything else constant, act as if everything else is just 0 for purposes of comparing the two, and we calculate 0.57 times 1,000 plus 0.008 times 1,000 squared, we get 8,500, and then we calculate the second version if the size were equal to 1,100 times 0.57 is 627, plus 0.08 times 1,100 squared, we get 10,037, so the difference is 1,730. So if this were our equation, the square term indeed would be pretty important. But since it's the log of size that we're squaring, we need to go back and double check and determine whether that's important. Finally, our last question asks us, if we wanted to compute the difference between the price of a pool when you have a view compared with without a view, how would we do that? How might we do that? Well, the pool with a view, we see that the change in log price is 0.002. So we don't have any intuition about whether that's a big change or not. One thing we can do is ask, well, how big would the change in price have to be for the log of, let's say, a $100,000 house to change, for the difference in the logs of a $100,000 house changing to be 0.002. So what would delta P have to be? What would the change in the price have to be? Well, we can go to R, and we can calculate the log of $100,000 and add $200 to it, and subtract the log of $100,000, and we get 0.00199, which is basically what we have as the coefficient. So then we say, oh, the house would have to go up by $200. Or the house would be expected to go up by $200. Well, that's a 2% increase if our base is $100,000, so that seems like not a very big increase on a $100,000 house. So a pool with a view doesn't really have a very big premium in this particular specification.